Okay. Here at the, not here to talk about use of extra citizen technology for code reuse using an open source project called Pyke. This is the outline of the presentation. We're going to talk about, first of all, thinking that led to Pyke, and then we'll give you an overview of what Pyke looks like, what the initial results of using this in the project were, and where we can go forward from here. So talking about the thinking that led to Pyke, this came from a contracting job I had where the contractor had many clients, almost the same code. They're copying the code a lot, doing little changes. They want to do a better job of code reviews. They also want to move to Python for better developer productivity. Inside of the Python program, they pulled me in and we said, okay, how do we do code reuse here? And the first question is, well, what is code reuse? And the answer to that question is whether it's functions. So initially I thought about, okay, so I've got a client, the first client with 2 functions, second client comes along, and maybe it can reuse the B function, but it needs a new A function. Well, this is easy in any programming language, and this leads to the first concept of code reuse. Libraries, which are just buckets of low-level functions that higher level functions you can choose to use. But there's another possibility, and that's that the client 2 can reuse the A function, but it needs a new B function. In this situation, our programming languages need to give us some help on what the programming languages can do. And the current solutions to this are all kind of revolve around object-oriented programming and image language. And some extensions of that, open data, generic functions, that sort of thing. All of these solutions are using trapping the call when the function A calls function B, and then making a decision at that point in time to figure out which B function to call. But those solutions all have a limitation, which I'm going to show you now. And to do that, we need to look at a little bit more complicated example involving 3 functions instead of just 2. Client 2 comes along, we need a new B function. That B function needs a new function, which is totally different than C, so we're going to call it the D function. Now client 3 comes along, and now things are looking better, all we need is a new D function. We write our D2 function. Now we want to call this program for client 3. How does that work? Well, obviously we're going to start at the top with the A function. There's only one of those. Now when A wants to call a B function, which B function do we use? All we know about client 3 is it wants to use the D2 function. So we're left to guess. We pick the first one, and when the first one tries to call the C function, then we discover this isn't going to work. And at this point in time, this shows the limitations of the current solution because the B1 function has already been executed. We can't undo the execution of that function to try the next function. To continue onward with the example, what we need to do is back up from the B1 function and try the second B function. When we do that, we discover that there is a way to construct a call graph for client 3. What we're doing is we're trying to construct a complete call graph for the client. And this shows us that what's needed are 2 things. First of all, the function selection should happen prior to calling any of the functions. This is very different than the dynamic approaches like object-oriented programming. And at first it may sound a little strange because in object-oriented programming I've got all these parameter data available to me that I can use to figure out which function to call. If I'm calling this prior to calling any of the functions, I don't have that data. It seems like that would be a limitation. It turns out it's a big deal. The second thing that we see here is that what you see with these little blue boxes bouncing around is exactly the algorithms used by backward chaining rule-based systems in the field of artificial intelligence, systems like Prolog. The problem with systems like Prolog is it's a very different programming paradigm than procedural programming like Python is. And how do you bring those 2 together is the question. So next we're going to look at how the backward chaining works, see how you can bring these 2 together. Here I'm indicating goals as dotted line boxes. We have find A goal, and rules as solid line boxes. There's only one A function, so there's only one rule here. For the find B goal, there's 2 rules. We have 2 B functions. We have find C and D goals. And then with expert systems, we're going to link the rules to the goals. And so the use A1 rule needs a B function, so it's going to ask for a solution to define B goal. So we're going to use B1 rule, it's going to ask for a solution to define C goal, and you use B2 rule, ask for a solution to define D goal. This is the structure of what the rules would look like in the rule-based system, and how it inference engine execute these rules. So if I ask it for a solution to find A, it's going to execute the first rule there. That rule says I need a solution to find B, so we're going to try the first rule there. That says I need a solution to find C, we're going to try that rule. But that doesn't work because we're going to be client 3 here. And so there's no other rules for find C, so the find C goal fails, which means that the use B1 rule fails. So we're going to try the next B rule. That means the solution to find D. Try the first rule there. That fails for client 3. We try the second rule, and we have a solution. And this is exactly the same thing you saw in the prior slide, which is why the backward chaining algorithm is the right algorithm for this approach. Now that we have this backward chaining rule set up here, then the question is how do we use this built function called graphs? And the way to do that is by attaching Python functions directly to the backward chaining rule. Then we can use the linkage to the rule that was developed during the inferencing to represent our function called graph directly. Okay, so in order for you then, what does Pyke look like? First of all, Pyke has its own syntax for defining rules that it compiles into Python source modules and then import. This allows you to put little Python code snippets in your rules that open up capabilities for doing things that are more easily done in a procedural language versus in a language like Prolog, you're kind of tied to only doing the backward chaining. And so the rules look like this. The green words are reserved words. The purple words are the goals. The pattern variables, if you're familiar with Prolog, are indicated with a $sign. The $sign line is a pattern variable. Within one rule, the use B2 rule, for example, the $client has to have the same value. The use B1 rules use the $client to have a different value for that rule. And rules are often referred to as if-then rules. And with backward chaining, the backward chaining proceeds from the then part of the rule backward to the if part of the rule, and then links that back to the then part of another rule opposite. And so oftentimes the if-then rules are written in a reverse order, the then part first, followed by the if part, which is what we have here. So the use clause is the then part of the rule, and the when clause is the if part of the rule. So if we want to read this as an if-then rule, you can start with line 3 or use B2 and say if, and then the check function says if version 2 of the B function is okay for this client, and the check function, if it doesn't know what B function to use, it will succeed to allow guessing. And line 5, we can find a solution to find B goal for this client. Then on line 2, the then part of the rule, we have a solution to define B goal for this client. And that's basically how these rule-based systems work. Similarly, I'm showing rules for the use D1 and use D2 rules here. The next question is, okay, now, how do we attach our Python code to this? And we do that by an additional clause which Pyke calls a with clause. And with the with clause, I can have any number of lines of Python code. I'm just showing one print line here. And these are all, you can have whatever Python code you want. The Pyke compiler does not try to parse these and understand these, it just copies these into the output Python source module. And so all I'm going to do here is the D1 function is just going to print that D1 got called, and the D2 function just prints that D2 got called. And that's okay so far. But when we go back to the next rule, the use B2 rule, we do the same thing there, put a print B2 on that rule. The problem here is on line 5, the find D goal is going to also have this Python function associated with it, either the D1 function or the D2 function, depending on the inferencing. And how do I specify in this B2 function how it's going to invoke this coordinate function? And that's done by including a line of Python code underneath the goal with a $sign indicating the function that's returned from the goal. In this case, the function takes no arguments, doesn't return anything, so we just call it a function. This would normally be how you invoke subordinate functions within a rule like this. In general, the when clause may have several goals that return subordinate functions, and each of those would have a line of Python code for a $$ sign in it indicating how to use the function return. And then what the Pyke compiler does is it takes all of these lines under the goals and adds them to the lines in the with clause, adjusting the indenting in that to form the B2 Python function that's going to be invoked. In this case, that's going to cause the D function to be called before we see this print B2. So we're going to see the print D before we see the print B2, which means backwards. And so Pyke provides an alternate way of dealing with this. And I can use this as clause to say I want the Python function associated with this goal to be stuck in a pattern variable. We're going to call that $P here. And then I can use that pattern variable in the when clause just as a function. This allows me to have control over when the function gets called, whether the function gets called, how many times the function gets called, all that sort of stuff. So it's a more general solution than the first solution I showed you. Now what we're seeing here is within the Python code, we're seeing this $P pattern variable. And that will be the Pyke compiler is going to substitute, all it does is scan these dollar variables and it substitutes a little Python expression that looks like that value. And this allows us also to use other pattern variables within the code. So if I want to have in my print statement which client is this B2 function was created for, I can cook that into a function like this. And that's why the lines of Python code are actually within the KRP source code, so that the expert system rules can configure these functions by setting variables within the function in addition to wiring the functions together to call back. To look more at these rules, if you want functions to, or parameters to your functions, your Python function, you can add a taking clause at the end of the use clause and specify your Python parameters there. The functions returned, Python functions returned from a goal are referred to as plan. The plan refers to the function wired to all of its subordinate functions, that complete tree that's called a plan. And you just execute that like a normal Python function. You can call that plan more than one time, as many times as you want. You don't have to rerun the inference engine each time. And plans may be pickled and reused. They can be reused within the same program or even within a different program. If it's used in a different program, that program does not need all Pyke imported into it. It just needs one small module. Pyke also supports overchaining rules. In this case, for each, because forward chaining rules proceed from the if to the then and then to the if of the next rule in the forward manner. They're written normally as the if first and then, so for each is the if part of the rule, and assert is the then part of the rule. The reason I'm using for each is because there's multiple facts listed here that may be matched in multiple different ways. And for each combination of ways that these facts match the patterns, the rule will be fired and all of the facts in the assert clause will be asserted. All of the forward chaining is done prior to any of the backward chaining within Pyke. The forward chaining rules can't call backward chaining rules, vice versa. But the backward chaining rules can use facts that were asserted by the forward chaining rules here. Pyke also supports a generalized knowledge of concept of knowledge bases. It has fact bases that simply store facts. It has rule bases to store the forward chaining and backward chaining rules. The rule bases have inheritance, so that you can inherit rules from other rule bases. This can go on to any depth. That's a single inheritance scheme, and that means that each rule base has a unique root rule base that is used to define a rule base category. You might have multiple root rule bases, but the name of the rule base category is simply the name of that root rule base. For each rule base category, you pick one rule base within that inheritance tree that you're going to activate for each execution of the inference engine. And you can pick different rule bases for different activations of the engine. You can use that, for example, if you want to have a few special rules for the client tree situation. You can have a client tree rule base that inherits all the rules from a default business rule base. You might also have a browser rule base that has an IE and a Firefox rule base that has some specialized rules within those. then you can choose which of these to activate before you call Pyke to create a plan. The knowledge bases also provide for extensibility. You can write your own knowledge bases that define the concept of looking facts up and proving goals in whatever way that makes sense for your application. And this is the way that you tie this backward-chaining rule-based stuff, which is very different than procedural stuff, into Pyke, procedural things like Python. Okay, the initial results. Once I had this thing, then I've got a complete expert system available to me. So I'm thinking, well, I can use that to automatically figure out database domains. I can give it some keys. I can give it some columns that I need. It can figure out how to do the tables together to get to this column, give them these keys. So I don't have to write SQL anymore. I can also use it with something like HTML templates. If the column names are put in the template, put these column values here, they could go through the template, find those names, create a program to render the template, as well as create all the SQL statements to go get the data all automatically. I wrote a WYSIWYG front end for this. It takes the environment information that comes into it, asserts all of that as facts for the inference engine. It does a proof on the process goal. Process goal for normal pages, outside like form action, has two main sub-goals. First, that's proven as a format retrieval sub-goal. This figures out which HTML template to use, reads the template in, goes through all of the values required by that template, creates a program to render that template, and returns as one of its, at the inference engine level, this $needed data descriptor, which is a list of column names that it's going to need. Then the second goal is the retrieve goal. That takes that list of column names. It can look up the facts in the environment to find cookie values or information in the URL for the keys for the table, and it will construct the SQL calls and create the Python programs that invoke the SQL commands and return a dictionary that has the column names and maps of values. The process goal then takes those two plans and executes them in the reverse order. So it's going to execute the retrieve plan first, which will return the data, and then pass that data to the plan returned in the format retrievable in order to render the template, return it to an HTML document. Then the WYSIWYG application just returns that HTML document as the answer to the question. You can see examples of this, some simple examples of this in the Pyke source code area that was examples directly. So the fundamental lesson learned was that Pyke is far more capable than I had first imagined. I was thinking, well, this is going to be something that's a little bit more adaptable, with kind of a library thing where you got this library you can pick between whether it wants to use B1 versus B2 somewhere in the library. That's going to help a little bit. But the results of using Pyke is you end up with something that's much more like a compiler backend that generates code. In fact, it generates the whole program. The difference is that the compiler front end is not a parser where you've got a programming language and you've got to write all this text to define what you want to do. It is going to parse and generate the code from. But it's an observer of already known facts. Show me your schema and I'll generate the SQL. Show me your HTML and I'll generate the program for you. So that's a very different feel from normal compiler. You're not having to write that code. This changes the whole concept of code reuse from static libraries, buckets of functions, sort of thing, to dynamic automatic programming. It ends up being more of an automatic programming. Or from silos of static functions, like here's some functions that deal with SQL, here's some functions that deal with HTML. Instead, you're going to have rule bases that encapsulate an expert's knowledge in SQL and as a rule base, which will generate SQL code for you using his expert knowledge. And you'll have another rule base for the HTML and CSS that will encapsulate an expert's knowledge and generate HTML and generate CSS. And you combine these different rule bases to produce more complicated programs. So it's more, instead of like code reuse, it ends up being more like knowledge reuse. And this is, I guess, a side effect of using the expert system, knowledge-based systems, out of artificial intelligence. Going forward, again, because of the backward chaining capability, it seems like there's lots of different areas that this might be applied to. And I'm just going to let you read through those here. When I was working as a contractor, I'm going to ramble on. When I was working as a contractor, I got to the point where I had the retrieve working. I was generating SQL statements to return unique column name values. I didn't have the multiple roles stuff done yet. I was just starting to get some really interesting results when the company that was running without a president hired a new president, and he came from a Java background, but he never heard of Python, and canceled the project, and that was the end of the contract. Right when it was getting into it. So what I've done is I've taken, I've re-implemented the expert system from scratch. So Pyke is actually the second generation of this thing. So I've incorporated a lot of the lessons learned from the first generation and placed out there as an open source project because I'm sure that there's other people that could take this and use it for doing interesting things. And that's why I'm here at PyCon, because those people are sitting out here in this room. And so up until this point, I've been flying completely solo. I was the only one working on this project at the contracting level, the only one working on the Pyke open source project. For Pyke to move forward, and Pyke is ready for early adopters. It's in the open state right now. It needs your help. I know a lot of people out there have different specialized knowledge in different things that they can encapsulate in rule-based with Pyke to generate systems that do automated programming for the users of those tools. The documentation is shown here. If you guys have any questions, I'll open it up to questions. Okay, so you're asking if I have a debugger to show how the inferencing is working and whether I can update the knowledge database? Yes. The answer, well, the debuggers, I've got a knowledge rule-based traceback module so that if you get exceptions, it will translate the Python information into the KRB information. So you'll see the lines from your KRB file where the exception occurred and translates it backwards to the source file that you use so much. I've also got tracing capability where you can trace individual rules, and it'll tell you when the rule gets invoked and when it succeeds, what values of pattern variables were when it succeeded, and when the rule fails, you kind of follow the inferencing that way. Also, for the reloading the rule bases, the whole knowledge engine is encapsulated as an object. There's a knowledge engine object, and when you instantiate that object, then it goes out much like Python does, and it checks the modification time on the KRB file versus the last set of Python sources that it's implemented. And if they haven't changed, then it just re-imports the same module. If the KRB file has changed, then it's going to recompile and generate new Python sources like Python does when you do an import. And you can do that multiple times within the same program, and it will pull in new copies of the database. Yeah. Pure Python.
So for the Mac, how are those Macs
the arguments for the facts are right now are any atomic Python value like number, strings, none, true, false, that sort of thing, or tuples of those, or tuples of those things, tuples of those. nothing really stopping you from placing, things like objects within an object, within a fact argument. But there's still a mechanism to do for pattern matching, to try to do special matching, have this pattern only match that kind of an argument. What you could do though, you could match it, you could say I want to match the third argument to be color X, match anything. And then within the when clause, you can specify a piece of Python code that does an is instance on $X to see if it's a certain class or something, or check for certain attribute value. And so again, you can insert little snippets of Python code within the inferencing logic to do things that are, like I say, already easy to do with CLI. Any other questions? Okay. I was wondering how many of you might be interested in trying to do some kind of a open space or other longer discussion on this. We have a few. Okay. Maybe we'll try and set that up on the open space support next. Another question?
Well, just to let you know, J2 is hosting an open space on Saturday, and as far as I know, it wasn't a few of us, and two of us, or maybe us, we would really enjoy it. We know that we talked about Pyke, because we're interested in adopting Pyke and automation. Maybe that would be a good place to start to set up our open space. We've got on Saturday evening. If you're interested in that, that'd be a good opportunity. We have the room.
Okay, so we just do it at the Gen 2 open space meeting then?
Yeah, above International Room at 8 a.m.
Okay, that's Saturday?
Yeah.
Tomorrow?
Yeah, 6 p.m.
Okay.
That work out for you as well?
Anyway, if that's a problem for us? Okay, that sounds like a deal. Thank you for your input.